A few important tips when we're dealing with these density curves is when you have your data, always plot it before you do anything else. Make a graph. Typically it's going to be a histogram or a stem plot because those are really easy to obtain. From that histogram or stem plot, look at the overall pattern. What's the shape? What's the center? What's the variability? Are there any outliers? Because that's going to tell us if we should do the mean or the 5-number summary. We use the mean and the standard deviation when we have a symmetric distribution. We use the 5-number summary when it's skewed or if we have outliers. Now, what we're interested in this section is this third thing when we have an overall pattern that is so regular that we're able to create one of these smooth curves for it. So these density curves, we can think of these as if we were drawing a curve through the tops of the bars in a histogram, smoothing out any of those irregular ups and downs in the bars. But there's a few distinctions between histograms and density curves that we want to recognize. The first one is that when we set up the curves to show the proportion of observations in any regions by areas under the curve. So in order to do that, we will choose a scale so that the total area under the curve is exactly 1. So that's really important here that we recognize that any region is giving us the proportion of observations. What fraction of the whole is in that region that represents the proportion of the observations in that region. Also note that a histogram is used to plot samples. A density curve is intended to reflect the idealized shape of the population. We don't necessarily know all of the population data, but we're trying to guess what it should look like if we did know the entire population. You can see here where we're looking at the body temperature in degrees Fahrenheit for an observation of 130 body temperatures. And if we're looking for the proportion of temperatures 99 and above, on the histogram, you would be looking at the area in the rectangles. In the density curve, you would be looking at the area in that curved shape that kind of looks like a triangle, but it's not quite a triangle. So we'll have to come up with a way to find the area, and we'll be using some special tables to help us with that. And the density curve and the distribution, the histogram, are going to be slightly different. And you see here that the number of proportion, or the proportion of observations in the blue region is 19 out of 130. And that tells us that we're looking at 0.146 of the total observations. Whereas with the orange section using that density curve, the area is 0.1587. So it's not exactly the same number, but they are pretty close. And so going from the sample to the population, you are going to get a few differences, but they should be relatively close. A few other things to recognize when we're looking at these density curves is that the area under the curve is representing the proportions of the total number of observations. Okay, that's so important. That's why I've said it twice now. But also remember that the median is that point where half of the observations are on either side. So the median is the equal area point. It's the point where the area on the left equals the area on the right. So the median on a symmetric density curve is at the center. On the other hand, the mean is that arithmetic average, and it's like thinking about weights on a seesaw. The mean is where the seesaw would balance. So here, the mean on a density curve is the point where the curve would balance if it was made on solid material. So it's not an equal area like the median is, but it's this balancing point where it's looking at all of the weights of all of the different values. Now, when you have a symmetrical curve, then it's going to balance at the center as well because the two sides are completely identical, which means that the mean and the median would be the same value on one of these symmetric curves. So you can see with this picture that when you have that symmetric curve, the median and the mean are at the same point, whereas on a skewed distribution, you will see that the mean is actually going to have to go towards that tail sum in order to balance out those weights. So the median is going to be the point where you have the same area on both sides, but the mean is going to have to be towards the tail in order to get things weighted. And so you can note that the mean of a skewed curve is always pulled away from the median and the direction of the long tail. Now, when we talk about this special distribution, the normal distribution, we're talking about a density curve that's symmetrical, single-peaked, and bell-shaped. It has this very familiar and distinctive shape, and that is the feature that makes it a normal distribution to look like this. And normal curves also have the special property where the standard deviation is shown on the curve where the concavity, where the shape of it is going to kind of change the look. So way you can think of this is think of this as a mountain. Imagine that you're skiing down the mountain here. So at the beginning, you're at a really steep angle as we're going away from the peak. But then, as you get down towards the bottom of the mountain, then it starts to level off. So it starts to grow flatter. That point where it changes from being real steep to being flat is exactly one standard deviation away from the mean. So if you look at these two graphs, you can see the horizontal bar showing you that it's one standard deviation to get from the mean to that point where it goes from being steep to being not so steep. And depending on the value of the standard deviation, you might have a wider curve or a smaller, narrower curve, because the standard deviation is telling us how wide or how narrow to draw our curves. So you can think of the mean as giving us the center of the curve and the standard deviation giving us the shape. If we change the mean, we're not going to change the shape, we're just going to change the location. But if you change the standard deviation, that will change the shape of the normal curve. Now, a few other properties for the normal curves is that a specific normal curve can be completely described by knowing the mean and the standard deviation. If you know the mean and you know the standard deviation, we know so much about this normal distribution that we know exactly what the shape of it's going to look like. And we also know all of the areas under it. So we've got the mean there at the center of symmetry, and then we have that standard deviation giving us the shape and giving us the distance from the mean to that point where the curve changes on either side. We're going to call this the 68, 95, 99.7% rule because in any normal distribution, we will have that 68% of the observations will fall within one standard deviation of the mean. So if we look at a picture, we see that if we go from the center here, and we go either one standard deviation to the right or one standard deviation to the left, that is capturing 68% of the data. Now, I'm actually going to adjust this a little bit, so you might want to add this picture because I find this one to be a little bit easier to use. We know that between -1 and 1 standard deviation, so that's within 1 standard deviation of the mean, that's 68%. But sometimes you'll find it more helpful to have that split up. So half of 68 is 34. So we can think of 34% of the distributions between the mean and 1 standard deviation above the mean, and then another 34% is between the mean and 1 standard deviation below the mean. Now, if we go to 2 standard deviations, then we'll have a total of 95%. And so you have that in your notes. If you got 2 standard deviations, you get 95. Well, what I want to do is to look specifically what's in these 2 sections. Well, we already have accounted for that middle 68. So what is left over? So you have 95 minus 68. So that means that we've gained an additional 27%. But you'll notice here that that is in 2 sections. So we need to divide that by 2. That tells us that there's 13.5% of data that's between 1 and 2 standard deviations. And then we can do the same thing to figure out what's happening when we go out to 3 standard deviations. And so in this little section, you will have 2.35% and 2.35%. And then finally on the very outside, you'll have 0.15% and 0.15%. So I'm going to continue to color code this so we can have these different sections. And then the last one actually goes on forever. And so we have this distribution I find to be a little bit easier to answer questions like we'll see in the example.